Alright, so in this video we're going to talk about kinematic hardening and the consistency condition. Before we start on that, let's just kind of briefly review kinematic, isotropic, and combined hardening rules. Specifically, we're going to look at the Ziegler kinematic hardening, and we're going to look at a hardening rule in deviatoric stress space, and we'll explain the difference between stress and deviatoric stress space. And then we'll derive the consistency condition for kinematic hardening in deviatoric stress space for the J2 yield criterion. Now, at the time of this recording, I have to go back and still backfill some particular lectures. So you may see some at a later date that come before this that describe some more aspects of plasticity. Specifically, I need to go back and talk about different aspects of the normality flow rule and things like that. This is a big part. So let's start off just first talking about what a hardening rule is and why we need it. So we need three items really in yield surface plasticity items, in yield surface plasticity theory. Now, there are other plasticity theories out there, endochromic theories and so forth, and they have a little different take on things. But for yield surface plasticity, we need something called a yield criterion. We are going to use J2, the second invariant of the deviatoric stress tensor. We'll list what that is in a little bit. And we need what's called a flow rule. And for us, that is the normality flow rule that we're going to use at this juncture. And basically what that says is that if you wanted to calculate the plastic strain increments, that they would be proportional to the partial of F with respect to sigma ij. So it points in a direction that is normal to the yield surface at that particular spot on the yield surface. And then you need to have a hardening rule. And there are lots of different hardening rules available. There are various kinematic hardening rules. Kinematic means movement, where the yield surface moves. Isotropic hardening rules, where you have an expansion of the yield surface. And combined hardening rules. And so we can look at each one of these. We're going to focus on kinematic hardening. And even with kinematic hardening, there's lots of different types of kinematic hardening models. There's linear kinematic hardening, there's nonlinear kinematic hardening, and so forth. We're going to go with kind of the classical approach right now. And if we understand that, then understanding the more complicated, maybe even you could say more sophisticated hardening rules is something that we can do after that. So with linear Ziegler kinematic hardening, what this says is that the movement of the yield surface, and what I mean by the movement of the yield surface is the back stress tensor, or some people call it a shift tensor, the d alpha ij would have some sort of proportion to, in deviatoric stress space, S minus alpha. So if we have a yield surface right here, and this was maybe over here was the origin of stress space, the vector that goes to the center of the yield surface is S. Our current stress point might be right here. That's what we're going to call S, the deviatoric stress. You can write it there as well. It's a little messy. And the difference between those is S minus alpha. And so what we're saying is that the yield surface is going to move. It's going to move its center. Maybe I'll use a different color. It's going to move its center along a path that joins S minus alpha. So this new yield surface, trying to draw these the same size, for an increment of stress along that direction, let's say, ds, will move along that path that joins this. Now that increment of stress doesn't have to be in that direction. That increment of stress can be in a different direction, but yet we still want to have an increment of the movement of the yield surface along the path that joins S minus alpha. There are different hardening rules that alter the path of this, and you can have different terms that go here, but those are some different names for those. For example, Morose kinematic hardening shifts that away in certain circumstances for highly non-proportional loading. For proportional loading, something like Morose kinematic hardening and Ziegler kinematic hardening reduce to the same thing. We can discuss those things as we dive into the details a little bit more in depth. All right, so if you've noticed, I've drawn this yield surface in deviatoric stress space. We can also formulate all of this in regular stress space. If you're dealing with an anisotropic material, then you might want to just go ahead and work in regular stress space. If you're dealing with a regular isotropic material that follows the von Mises yield criterion or the J2 flow theory, the nice thing about that is the yield surface plots as the 9-dimensional hypersphere in that space. The geometry comes a little bit easier and maybe you could say regular in that particular stress space. So we're going to work right now in the deviatoric stress space. So let's talk a little bit more about the yield criterion, and then we'll get into the details of the hardening rule. We'll leave the flow rule to another video that will precede this one at a future date. All right, so let's kind of refresh ourselves just a little bit on what I mean by J2 flow theory. So J2 means the second invariant of the deviatoric stress tensor. And the deviatoric stress tensor S can be defined as sigma minus 1/3 the trace of sigma times the identity tensor, or if we want to express it in a little bit a different way in index notation, Sij is equal to sigma ij minus 1/3 sigma kk Kronecker delta ij. Alright, so basically it removes the hydrostatic stress terms off of the normal stress terms from the stress tensor, and we're left with Sij. And the second invariant of the deviatoric stress tensor, because we can show that the trace of the deviatoric stress tensor is 0, the way we define this, if I use my index notation, skk will be adding up to V0, and that leaves the second invariant of the deviatoric stress tensor to be 1/2 Sij Sij. Now, as a yield criterion, yielding will happen when this particular value is equal to 1/3 sigma yield squared. Or if I rearrange this, I can write this as Sij Sij minus 2/3 sigma naught squared equal to 0. And I'm going to call this my yield function. I'm going to define this as f. Again, based on our index notation and our summation here, there are actually 9 terms. I've done this recently, but I'll go ahead and write these out. S11, I repeats and J repeats. We end up with 9 terms that look something like this. Now I am writing this as if it is fully non-symmetric, and I think that's the best way to deal with this because of the partial derivatives and things. You just need to be a little bit careful. Oops, we'll go minus 2/3 sigma naught squared equals 0. And so, as you see, this is effectively the equation of a circle, and that's why my yield surface is circular in my picture, trying to draw that. And of course, this term over here, 2/3 sigma naught squared, here sigma naught would be my axial yield stress, beyond which I start to have plastic flow. So again, this forms a surface. Inside of the surface you have elastic material behavior. As you move away from the surface, you begin to have plastic flow. And the deal with a consistency condition is, in yield surface plasticity, the stress point can either be inside the yield surface or it can be on the yield surface, but it cannot go outside of it. So let's write that down. So the stress state must either be in the yield surface. That's where we have elastic material behavior for elastic plastic materials, or the stress state is on the yield surface. And even if this yield surface moves, this stress state, this stress point, must maintain itself on the yield surface during plastic flow. Okay, let's change colors. So we can say the condition or the requirement that the stress state stay on the yield surface during continued plastic flow is the consistency condition. Okay, and so you'll see that term quite a lot. We're going to derive the consistency condition, and that will help us figure out this value of d mu up here. Alright, so at this point, let's be just a little bit more careful with our terms. As I have it in my picture, the tensor alpha is my backstress tensor in deviatoric stress space. Now, most people use the same symbol, alpha, for the backstress in regular stress space, the sigma. In regular stress space, our yield surface for the von Mises criterion will plot as an ellipse. And there's a center to that ellipse, and this, from the origin of stress space to the center, is the regular alpha, and this is the deviatoric. So you have to be kind of careful. You have to kind of look at the context of the problem and or the paper or whatever is being written, in order to ascertain whether you're in regular or deviatoric stress space. So just my advice is be a little cautious about that. The way that the consistency condition works is very similar in both cases, but we need to ensure that as this increment of stress or deviatoric stress is applied, that the alpha moves with an appropriate increment, and we are specifying it for the Prager-Ziegler hardening rule that it moves in the direction of S minus alpha. Alright, so let's talk about this. Let's define the rest of these terms. So here S is our deviatoric stress. And if I want to define the term S minus alpha, see that's that vector here, S minus alpha, I'm going to define that as xi. Okay, so if my yield surface is initially positioned at the origin of stress space, then I have 1/2 Sij. Sij is equal to 1/3 sigma naught squared. But since that yield surface can shift away from the origin of stress space, my yield criterion then is going to be expressed this way. Xi ij minus 2/3 sigma naught squared equal to 0. This is my yield criterion now. When my back stress is not equal to 0. And that's fine. That's perfectly fine. Now what happens when we're on our yield surface is that this yield function f equals to 0. Okay, if it is less than 0, then we're inside of our yield surface and we can't get bigger than 0. Alright, so if I'm on my yield surface, this thing is true. So what we're saying is that the function of S in alpha is equal to 0 on the yield surface. And if I apply an increment of stress, and I have also going with that an increment of my back stress, even during that whole movement and application of that stress increment, that yield function must still be 0 if I'm loading my material. So what that says is that S plus ds and alpha plus d alpha also have to be 0 during my plastic flow. Either neutral loading or loading. Alright, let's look at this in a little bit more detail. Alright, let's expand this bottom term that I have here out. So I can write this then as the function of S comma alpha plus the rate of change of that function with respect to S times ds. Okay. So that's the rate of change and then the amount of change. And the increment gives me the total amount of change. And then also a partial derivative of that function with respect to alpha, d alpha. And so this is just the same thing, just expanded out by the use of calculus, and that has to be equal to 0. Now this term, this first term right here, is 0. So what this is telling us is that the partial derivative of f with respect to s ds is equal to minus partial derivative of f with respect to alpha d alpha. Now our J2 flow theory is what we have up above, xi, or s, oops, I said s but wrote xi, s minus alpha dot product s minus alpha. You can think of it as a dyadic for tensors, or a dot product if you like to think of these expressed in terms of vectors. And it's convenient sometimes to think of that. But minus some sort of constant. For us, it's the 2/3 sigma naught squared equal to 0. Alright, so let's take the derivative, or the partial rather, of this with respect to s, and the partial of that with respect to alpha. Alright, so basically we have these terms, and they come off like squared terms, like I had written up there, s11 squared, but now it's going to be s11 minus alpha 11 quantity squared. So if we take the partial derivative of that with respect to s, that's going to be 2 s minus alpha, and the derivative of the stuff on the inside, partial derivative of s with respect to s, which is going to be positive 1. Alright, and so then if we take the partial derivative of that same function with respect to alpha, we're going to get a 2s minus alpha. And because it's minus alpha, we're going to take the partial derivative, we're going to have a minus sign right here. So the bottom line with this is that the partial of f with respect to s is the same as the negative partial of f with respect to alpha. Okay, so let's keep that in mind for the next step. Alright, so we're going to start with this line. The partial of f with respect to s ds plus partial of f with respect to alpha d alpha is equal to 0. And what we're saying up here is d alpha, if we write it in this vector form, is equal to d mu times s minus alpha. Alright, so we're going to use this and this into this equation right here. Okay, let's see what we get. We have the partial of f with respect to s ds plus the partial of f with respect to alpha d alpha, but what we're going to do is we're going to write this as the negative of the partial of f with respect to s d alpha. We're going to use d mu s minus alpha. And there's a dot product here and here. So if we solve for d mu, let's see what we get. The partial of f with respect to s ds is divided by, oh, this is equal to 0, divided by the partial of f with respect to s minus alpha. Or in index notation, partial of f with respect to s mn ds mn divided by partial of f with respect to, let's use KL, skl minus alpha KL. Okay, now this is in deviatoric stress space. Now, so this is the scalar constant that multiplies by this term to determine what the movement of the center of our yield surface will be. And just to be clear, let's go ahead and expand out these terms on the top and the bottom. I'm going to call this the numerator In the denominator, let's expand those terms out just to have it written down. Right, so like I said, there's either a dot, well, here we don't need a dot product because of the summation notation, but the numerator of this is going to be partial of f with respect to s m n, let's use our numbers. I may not write them all down. We'll get started. D s11 plus the partial of f with respect to s12, ds12, and so forth, till finally we get to the partial of f with respect to s33, ds33. In the denominator, is similar terms, partial of f with respect to s11, s11 minus alpha 11, partial of f with respect to s11, s12, s12 minus alpha 12, and so forth. We get the 9 terms. So we get to the partial of f with respect to s33, s33 minus alpha 33. Okay, so we have all of those terms in there. And of course, if we know that we're using the J2 criterion, we can explicitly find the values of the partial derivative of our yield function with respect to S11. And the handy thing about that is if we use 1/2 Sij, Sij, okay, and that's equal to, of course, we'll do a couple terms here, like S11 squared, S12 squared, and so forth. If we do that, then the partial derivative of f with respect to, for example, S11 would be equal to S11, and so forth. So in other words, the partial derivative of f with respect to Sij, when we use the function in this form, is going to be equal to Sij. So that makes this even easier to deal with because of the way those partial derivatives work out for the J2 yield criterion. For other yield criteria, you'll have a very similar development of the consistency condition for kinematic hardening. Some of these terms may not work out quite this conveniently. The other thing I want to point out is if we look at the term here, for kinematic hardening, the yield surface stays the same size, so that is a constant. For isotropic hardening, that does not stay the same size, or for combined kinematic isotropic hardening, that does not stay the same size. So you can have terms in there that will show up in the consistency condition. All right. So with that, now we have a description on how to move our yield surface, and let's talk about some of the issues with that while we're here. Alright, so here's a yield surface as we're here, and we're going to do something that's called proportional loading. Now, proportional loading means that all the stress components increase at the same rate as a function of time. And I can show this as a straight line in this deviatoric stress space. So it can be, remember this is in 9 dimensions, I'm just drawing this flat, maybe it's out to this spot right here. Okay, so we're going to get to this point up until which we have elastic material behavior. Now we start to have plastic flow. Plastic flow is in the direction that's normal to this yield surface by the normality flow rule. And we're going to apply an increment of stress. And while we apply an increment of stress, our back stress has to move along the path that joins this S to this alpha. And the new yield surface has to always maintain its spot. So kind of a poor circle. That's supposed to be a nice circle, but it always has to maintain its spot during the plastic flow. So basically, for proportional loading in kinematic hardening, this is just moving along this path to get to this point. In fact, if you want, you can back calculate where this thing has to end up. It's got to end up along this path with a radius. But what gets to be a little bit more tricky is when we no longer have that radial path. So we can cycle this back and forth all we want, and we're still in proportional loading, and we just go along that same path with our d alpha. Let's take a look at another situation where maybe we have done some stressing to this. The origin of my stress base is starting here. My yield surface has gone over here somewhere. Maybe this is my point that I have where I have finished this loading. Let's see if I can get there. Okay, so that's my S. My back stress is positioned in the center of this. So this red line is parallel. It's right on top of the blue line. That's my alpha. And now I'm going to take another excursion that's maybe off in this direction. And I'm going to end up over here. Now all of these points, again here, are elastic unloading. We can check our loading condition. I'll have another video for the loading condition. We can check our loading condition and see that we have elastic unloading. But now we're starting at this point, and from that position to this spot right here, this is my new xi that I have, and I'm going to add an increment of stress. It's in this direction, and I need to move my yield surface that goes along the direction of xi, yet maintains contact with this point right here. Okay, so my new yield surface may end up being here, and let me use a different color. It's moved along that path, and it's got to touch this point. So what does that look like? It's not quite in the center. It's going to be hard for me to fix that, but you kind of get the idea. It's got to be on this point. So now the next step is, now that it's here, this is my new xi, and I move along this path until I eventually approach this point right here. Now, I'm drawing these as finite increments. I'm really drawing these as delta s's, but we want to get as close as we can to ds's. So you need to make small increments in incremental plasticity. Errors can build up with finite increments, but if you're careful and keep track of everything, you'll get pretty close to where you need to be. It is possible to integrate along these non-proportional paths to come up with your position and your plastic strains. It can be difficult for very generic loading, but there are certain paths that can be done in closed form. Well, with that, I think I'll leave this, and I want to use this as the setup to calculating the movement of the yield surface and plastic strain increments for our non-proportional loading path.